Two types of carbon occur in nature, carbon-12 and carbon-14. Carbon-12 is stable while carbon-14 decays exponentially over time. When an organism which breathes in carbon dies, the carbon-14 decays while the carbon-12 remains unchanged. The carbon-14 decays exponentially according to the equation Q equals AE to the power of B times T, where A is the initial amount of carbon-14, Q is the quantity of carbon-14 that remains after a certain time, T is the time in years, and B is a constant. Now, in a previous video we looked at graphs of exponential functions. Here the independent variable is t, so I've just changed x to t. The function is called Q of t. It stands for the quantity of carbon-14 remaining in an organism. We're dealing with exponential decay here, so that means that b, the coefficient of t, will be negative. So we will be dealing with a decreasing function of time. So I explained the shape of this graph in a previous video. So as t increases, q will decrease. It will decrease exponentially towards zero. So this is an example of exponential decay. Now we also explained that this number here in front of e is the y-intercept of the curve. So the y value of this point is little a. Find a constant b if the half-life of carbon-14 is 5,730 years. Now the half-life of a radioactive substance is the time taken for it to reach half of its initial. I will just use this function here to explain half-life. Initially the amount of the substance is 4. Q at time 0 is 4. We're interested in seeing how long it takes for that quantity to be halved. That is to go from 4 down to half of 4, which is 2. And you can see here from this picture that it's about 0.46 seconds or hours or whatever the unit of time is. Now, it's a fact that the same time will be needed to halve the quantity further. So to go from 2 down to 1, the same amount of time is required. So I just move this point down so that we bring it down to 1. Well, that's as close as I can get. So we get 0.92, which is about 2 times 0.46. And to half the quantity further, that is to bring it down to we want a value of 0.5. Half of 1 is 0.5. There it is. So we add another 0.46 onto 0.92. That gives us about 1.39. So I'm allowing for rounding error here. Half of 0.5 is 0.25. So it could get half of 0.5, and that'll take a further 0.46 units of time. So, half-life is the time taken for half of the substance to decay. For dealing with a radioactive substance, decay might mean that it's being transformed into another substance. It could mean that it's an element being transformed into another element, or an isotope of an element being transformed into a different isotope of the same element. But anyway, we don't have to worry about the chemistry or physics of it. It doesn't matter what the amount is. If we're dealing with the initial amount, then we're dealing with A, and we're interested in the time taken for A to go to half A. So we want the time t that it takes for that to happen. But of course we don't have to start with A. We could start with any amount, as we saw in the picture. In the picture we saw that A was 4, and we wanted the time for the substance to go from quantity of 4 to a quantity of 2, and we saw that the time was roughly 0.46. Now actually in this question we're given the half-life, It's 5,730 years. And we have to work backwards. So we have to work backwards to find a constant b. So let's go to this formula here. Well, q at time 0 we know is a, but q at the half-life time, that's 5,730 years later, is going to be half of whatever a is. We don't know what a is. But, of course, we can use the full formula to get an expression for this here. We just plug 5730 in for t in this formula. So it's going to be ae to the power of b times 5,730. Or we can write it like this, 5,730 times b. So here we have this equation, which we can solve to find out what b is. Because the a's will cancel from both sides. So it doesn't actually matter what a is. We don't know a yet. We'll find that later from other information. But anyway, we have to solve this equation. So we divide both sides by a, and because what we're looking for is an exponent or a power, we take the log of both sides. So take the log of the left hand side. ln means log to the base e, as we've seen before. And we take the log of the right hand side, ln e to the power of 5730b. Now ln is log to the base e, so we've log to the base e of e to the power of something. That just gives us the power. So these functions, as we've seen before, are inverse functions of each other. So we just get the power. Now at last we can find b. We just divide ln of a half by 5,730. Here is ln of 0.5, happens to be negative. Well, actually b is going to be negative because we're dealing with exponential decay here. So q will decrease with time. The quantity will decrease with time, as we saw in the pictures. So we want to now divide this by 5730. Okay, we get this horrible decimal here. But in this question we want to write the answer in the form minus ln of p over q, where p and q are natural numbers. So I won't be using the calculator here. We have b equals ln of a half divided by 5730. Now, ln of a half is not the form that we want our answer in. We want ln of some natural number. A half is not a natural number, so we use one of the rules of logs that we covered before to write ln of a half as ln1 minus ln2. Ln of the numerator, which is 1, minus ln of the denominator, which is 2. Now the ln of 1 is 0, because any number to the power of 0 is 1. Log to the base e of 1 is 0. So we end up with this here, 0 minus ln2, or just minus ln2 over 5730. So now it's in the form minus ln p over q. We can see that p must equal 2. So that's a natural number, and q, the other natural number, is 5,730. Now I can't show a precise picture of this function yet because we don't know what a is. We need more information to get a. Using this constant, that is b, compare the ratios to 3 decimal places of the rate of decay dq dt of carbon-14 when t equals 4,000 years and t equals 1,000 years. So here's a rough sketch of q versus t. So initially when t is 0, q is little a, which we have yet to determine. But in this question we're going to get dq dt at t equals 4,000 and dq dt at t equals 1,000. So 1,000 might be somewhere here. So we're getting dq dt, that is the slope of the curve at t equals 1,000. That is the slope of the tangent to the curve at t equals 1,000. So we will be getting the slope of this line here. And we're going to compare that slope, or that rate, to the slope at t equals 4,000. That's at this point here. By the way, you can see that both of these lines have negative slopes. So for exponential decay, where b is less than 0, as you can see, this is actually a negative number. We have a decreasing function. The derivative will be negative. So dq dt is always negative, actually. If the function is decreasing everywhere, which it is. So here's q. Let's get dq dt. So I won't bother plugging in for b yet. Let's leave it as it is. Now we've covered how to differentiate these. A is just a constant in front, it's a constant factor, so we just leave it there. It's not added to this, so we leave it here to one side, and then we look at the derivative of e to the power of bt. Well, when you differentiate e to the power of something, we just get that function. But now we have to use the chain rule, because the power is b times t. The derivative of a constant times t with respect to t is just that constant. It's just b. So there's the derivative. So when you differentiate e to the power of something, you just write it down and you multiply it by the derivative of whatever the power is. So here's a formula for the derivative of any time t, but now we're interested in the derivative at two particular times. T equals 4000 and t equals 1000. So plug 4000 in here, so b times 4000 or 4000b. So I've just moved it over here, and now look at dq dt when t equals 1000. So we just plug 1000 in for t, and this is what we get, and we want to get the ratio of these two rates. So the ratio when t is 4000 to the ratio when t is 2000. So we take this ratio here, this expression here, we divide it by this, and you can see what happens. If I divide this thing by this thing here, I won't write it down again, I'll just show the division line. The a's cancel, the b's cancel. We get e to the power of 4000b minus 1000b. That's e to the power of 3000b. Okay, we've the same base here, so we just subtract the powers, this power minus this power. So this is what we get. Next we can just plug in for b and evaluate this thing. To 3 decimal places, this works out to 0.696. So in other words, the slope of this tangent here at t equals 4000 is 0.696 times the slope of the tangent at t equals 1000. That makes sense because at t equals 4000 you can see the rate is smaller. The slope of this line, the magnitude of the slope of this line is obviously less than the magnitude of the slope of this line. This line here is less steep than this one here. So the rate of decay is slowing down as time goes on.